as El Papapoyo on Twitter, and this is Practical Functional Programming. So very briefly about me, I work for Testable as a remote software developer and consultant, and we believe software is broken and we're here to fix it. So our mission is to improve how the world builds software, and we like to do that by not only working alongside your team to help you get stuff done, but also to help your team improve and grow. So if you're interested in learning more, you can check us out at testable.com. And I'm also the author of a book called Programming Elm from the Pragmatic programmers. And it takes you through starting off with Elm, learning syntax, going all the way through building applications, single-page applications, testing, performance, and all that cool stuff. So if you're interested in checking it out, you can visit bit.ly/programmingelm. So what is functional programming? There's a lot of terms that you probably have heard or thought of before, like pure, total, idempotent, monad, functor. I like to call it easier to reason about oriented programming. Side note, I was kind of disappointed there's not a tongue-in-cheek emoji. But seriously though, these are really cool concepts with fascinating mathematical backgrounds. And we're going to have a lot of cool talks today. They're going to dive in deeper to these concepts and they're going to blow my mind too. So I'm really excited. But I believe there's kind of a gap between sort of the theory and all these concepts and what they mean and really the practical application of them and what they mean when it comes to just doing software engineering and building apps. So let's fix that today. So we're going to divide this talk into 6 sections. We're going to focus on some problems and see how we can apply functional programming concepts, just building up from the very basics to more complex stuff, and see practical applications of these types of things. So let's start off with this one, and that's testing code, specifically code that is really hard to test. So we're going to use a lot of JavaScript code examples. We'll also see some Elm code examples later, but when you see this, it's our lovely language, JavaScript. So this is a function called Preorder details. It's an async function. It takes a list of IDs, and it's going to fetch the orders by IDs and print them out to the console. So just very briefly highlighting what we're doing, we're going to generate a URL based on the IDs. We're going to join them together with the join method. It's an array. Then we're going to await the order. This is an async function, so we're going to fetch all these orders, get back the orders, and then finally we're going to loop through all these orders, get the ID, date, and customer off this order, and then create a string of details that we can print to the console. So pretty straightforward, but how would we go about testing this function? So if we look at our test code, we're going to probably have something like this, and the biggest thing we're going to have to worry about is we're going to have to do a little mocking here. So I'm going to have to mock out my dependency where I fetch JSON. I got to replace that with a mock dependency with testable.js, and also mock out the console log that's in the global console. And then I'm going to require my Preorder details function, which is the thing under test. But I already have to do this setup where first I got to mock out the dependency, then I got to require the thing that's under test to make sure it uses the mocked out dependency. So you're already seeing the problems that are manifesting here. And then afterward, I got to make sure I clean up after myself. We set my dependency box, as well as restoring the console.log. Now when I go down to my actual test, then I got to take my mock and I got to make sure that when I call this fetch JSON with a certain URL that I'm going to resolve with this fake data that I'm going to use for my assertion. And then I'm going to make sure that I await the Preorder details when I call it. Unfortunately, it's an async function, it returns a promise, so I got to deal with this asynchronicity within my test as well. And then finally, I can go about making my assertions, and I'm just going to verify that I called that console.log mocked out dependency with the 3 order detail strings. So this is really problematic. We have to go through a lot of steps. There's some important business logic here of translating orders to this detail string, but it's kind of messed up with all of these separate things I'm having to do with this asynchronous function, and it makes it really hard and annoying to test. So the root cause comes from this problem of side effects. Or if you're not familiar with side effects, it's this idea of a function is going to produce effects on the outside world apart from just the return value of this function. And that can be problematic for a lot of reasons. Now if we return back to our function, we have 2 primary things that are making this problematic. First off, we have the fetch JSON. That is a side effect where we're affecting the outside world by asking it for some information. The other one is when we're printing to the console, we're changing some standard out state by printing to it, and that's another outside effect that we're causing. And really this causes this problem where our code becomes less predictable because it has to do this extra work, and so I can't trust this function to do the same thing every time I call it. It's non-deterministic. This also leads to a different problem where we saw it's harder to test, so we have to go through the pain of setting up these mocks and then afterward kind of decontaminate ourselves from, oh, mocks. But we all know this pain. So this really drives at what the heart of functional programming is. And we could reduce it down to just saying it's just programming with functions. Now, there's a lot more nuance to it than that, but I think this is the essence of what we're driving at with functional programming. So when I say that, what do I really mean by a function? Well, there's a couple things. First off, we have the idea of a pure function. So I'm going to use an ES6 arrow function here, a very basic function called add that takes x and y, and it returns x plus y. But this function is pure in that its output only depends on its arguments. It doesn't produce any of those side effects. So this function is predictable, it's testable. When I call add with 2 and 3, I always expect to get back 5, and I can trust this function to do that for me. Now another property of these functions is that they're small, and they're like building blocks, so to speak. So we want to think of functions, think of our programs in terms of small little pieces, these functions that are pure and testable and predictable, and I can piece them together to create more complex functions and more complex programs out of it. The idea being my whole program can then become predictable and testable. So let's apply that back to what we were dealing with earlier. So one of the problems is we had our core business logic kind of muddied up with these side effects. Let's try to break that apart and make it easier to test. So let's start off with the URL. We can make that into a very simple helper function. It's just going to take the array of IDs, it's going to return a string, and we'll join the IDs with that delimiter with a comma. We can have another helper function that's only responsible for taking an individual order and converting that into that string details. So we're going to use ES6 destructuring here to take out the ID, date, and customer to produce that string. And then finally, our main business logic was to take a whole array of orders and transform them. So we'll start off with this details for orders function. It takes the array of orders, and we'll just build up an intermediate array for now called details. And then we'll go through a for loop and we'll push the details into this array. And we're going to call to our helper function called order details. And then finally return this array of details. Now if you're cringing a little at this for loop, don't worry, we're going to return back to that in a moment. But we'll start with this for now. So when it comes to testing this code though, with the URLs, it's a pure function. I'll just go call it with an array of 1, 2, 3, and I expect to get back this string of orders with IDs 1, 2, 3. That's super easy to test. When I want to test the other function, order for details for orders, I just pass in a fake array of orders, and I expect to get back an array of strings. No mocks, no asynchronous functions, and that's my business logic. That's what's the critical part of this, and it's super easy to test with pure functions. Returning back to our print order details function, I can swap out those important pieces with my pure functions and just let this function focus on coordinating those pieces for me, because let's not kid ourselves, side effects are still going to exist in some form or fashion, but we just want to push them out as far as possible so that our core business logic is easily testable. So I can call the URL function I wrote with those IDs and let that handle that business logic. Then I fetch the orders, and when I get them back, I'll let the details for orders take in that array and transform it into the array of strings. And then I can just do my last side effect of looping over and printing these out to the console. So this idea is really, really awesome, and it was proposed, I believe, by Gary Bernhard. He named this in his talk Boundaries, this idea of functional core imperative shell, where you want most, if not all, of your business logic in pure functions. This was a Ruby talk, so it's pure methods, but the same concept applies. Something that is easily testable. I don't have to make out a ton of mocks for my side effects. And then wherever my side effects need to reside, that's sort of in a shell outside of this functional core. And it's just going to coordinate these dependencies for me. And that makes it easier to test our code. So the next problem, hard to follow code. So what do I mean by that? So let's return back to the details for orders function. We have this for loop here. So this is a little problematic, especially if you're already familiar with functional programming. You're probably wondering, why did I pick a for loop here? So one of the problems here is this code, it's not immediately evident what's going on here. I have to read through it, see these steps, and realize, oh, that for loop's just iterating through the array, and we're going to transform the array and make a new one that has the details for every order in it. But that's a lot of steps and instructions that we have to provide to the computer. So this code isn't very self-evident or clear what's the ultimate goal we want to accomplish here. So this is what we would call imperative programming, where it's just about providing a set of instructions to the computer. It's like we're telling the computer, here's how to do something. And the computer really doesn't know what is our ultimate goal that we want out of that. So we can contrast that instead with a declarative style of programming, where instead of telling the computer how to do something, I'm going to tell the computer what I want it to accomplish. So instead of being interested in what the engine of the car looks like, how all the pistons and pieces work together, I just want a car that looks nice and drives fast, and that's what's important to me. So if we apply that concept to details for orders, we can actually reduce it down to just this one line. This is a map method on the arrays prototype, and if you're not familiar with this method, it's going to take a function, and it's going to apply that function to every item in the array and transform each item into the new value inside of a new array. But what's declarative about this is I'm just declaring, here's the result I want. I want a new array that's been transformed according to this order details function, and I don't have to provide the series of steps. So visualizing this, when I use the map method, it's going to handle that iteration for me. It'll take the array of orders, and it's going to apply that order details on each order one at a time and add the result to the array. So we get the first order, we get its details. Then it proceeds to the next item and transforms it. And then it goes to the last order and transforms that. So it's handling all the steps of iterating through the array. I don't have to provide that anymore. And my code is a lot clearer to follow and understand what's going on here. So under our third problem, my code breaks unexpectedly. Now, there could be a host of different reasons why this might happen, but we're going to focus on one thing in particular. So don't shudder too much. This is a class. It's a person class. It's got a constructor. It takes a name and hobbies, and it stores both of those on the instance. And then it has a describe method. So this describe method is just going to check what kind of hobbies this person has. And if we don't have any hobbies, we'll just return that this person doesn't do much. Now, if we do have hobbies, we're going to take the first two hobbies, and then we're going to call the join method again, and join them together with an and in between them. And then we'll print that out, or return a string that says that this person likes to do things such as whatever those first two hobbies are. So now if I was to use this class, I could create a new person. I'll just use myself, and I'll provide a few hobbies like programming, reading, playing music. And then I'll call the describe method. And so it'll return, Jeremy likes to do things such as programming and reading. Well, let's say later on I call it again, and now I get, Jeremy likes to do things such as playing music. Well, that doesn't seem right. I'm supposed to have 3 hobbies. Where are the first 2 hobbies in that result? So if we return back to the code, this is our problem. I accidentally called a splice method. So if you're not familiar with this method on JavaScript arrays, it is going to, in this case, I provide 2 indices, 0 and 2. It say, give me back the first 2 items in the array. But it will also change the original array. So it actually takes out those first 2 things from the array, leaving only the last remaining item in the array. So when I called person.describe again, I got back only that one remaining hobby of playing music. So the root problem here is that I'm dealing with mutable data. And what that means is it's just data that can change in place. That would be a JavaScript object or a JavaScript array where I can add items to the array, or for objects I could change their properties, add properties. And the problem with this mutable data is that because it can be changed in place, there's nothing safeguarding me from my data changing underneath me, some rogue method changing it unbeknownst to me. And so that leads to subtle bugs and issues that we may not expect. So coming from the functional world though, the way we can fix this is to have immutable data, and most functional languages have immutable data by default. So with immutable data, our data can't change in place. Arrays can't have new items added. And this gives us safety and consistency because our state can't change underneath us, and we don't have these unexpected bugs cropping up for us. So we could fix our class by doing something like this. So when we accept the hobbies in our constructor, we could call a method called object.freeze, and this comes from ES6. And it takes, in this case, the array, and it freezes it so that I can't add items to it, I can't remove items to it. It becomes immutable, unchangeable. And that means here, when I hit this line in my describe method, it's actually going to blow up and throw an error. It's going to say, cannot add or remove sealed array elements. So now I can say, oh, I'm using the wrong method here. I meant to use slice. So slice does something very similar. We're going to give it an index and a length, and it's going to return the first two items, but it will not change the original array. It'll leave it intact. And immutable data ensure that this bug didn't crop up. Now, it's unfortunate that I had a runtime error, but we'll get to that a little later. Now, building on this idea of immutable data, data that can't change to prevent bugs from happening, is we want to talk about how do we change that state then. If it's immutable and I can't add items to an array, then how am I going to do anything useful with that array? So let's say with my person class, I want to add in new hobbies later on. Well, with immutable data, we don't want to change state, we always want to create new state. And so let's see what that kind of looks like. So I'm going to make another adjustment here. And it's kind of related to this idea of, so we have this class instance. And one problem with that approach is that we're hiding all of our state behind a class. And really with functional programming, we want to expose our state. We want to keep it out in the open, especially as we want to create new state instead of mutating it. So I'm actually going to change this now from a class to just a plain old JavaScript object. So I have a create function that takes the name and the hobbies, and it just returns an object with the name and the hobbies. But I'm also going to call object.freeze on both the object and on the hobbies to make sure that they're both immutable and can't change underneath me. Next, we can have our describe function. It just takes this person object, and it does the same thing that we did with our person method on the class earlier. So nothing too new or strange there. But now we can add on this add hobby function. It'll take a new hobby, and it'll take the person object, and we can't change state, but we always want to create new state. So we'll just create a new object. We'll call object.freeze again to make sure it can't change. And then we'll use some nice features that are coming from future versions of JavaScript. In this case, it's the object spread operator. So you can imagine if I always had to create new state and I had an object, I'd have to copy all the old properties over, and that could get really cumbersome. So with the spread operator, I can basically spread out all the original properties on person, essentially copy person, and then use that new copy. And then I can provide any changes I want to make here. So in this case, I'm saying copy the person and then provide a new array of hobbies. I'm going to again use that spread operator with the array here to copy all the old values from the original array and then add in the new hobby at the end of this array. And again, I'm going to freeze this to make sure it stays immutable. And now when I want to use this code, my state is out in the open now. It's not hidden behind this class instance. So I can create an instance of a person just by calling this create function. In this case, I start off with no hobbies. And now I can use my new add hobby function. I can call it the programming and the person, and it's going to return back a new person. So I'm always explicitly accepting my state changes because state always comes back as a new instance. And that keeps my state out in the open. I have an explicit flow of state throughout my program. And then I can add in another hobby, and then call describe, and I get back the same result I had before. But now, because I'm using immutable data and my state's out in the open, it's easier to follow the flow of changes in my program, and I don't have to worry about any method or function accidentally mutating my state underneath me. So now on to our fourth problem, too much code. Now this is a little ambiguous, so we're going to look at examples and see what I mean when I say too much code. So let's say in our application we're working on internationalization. And this is a very basic example, but we have a greet in English function and a greet in Spanish function. They both take a name and they return hi or hola with the name. Now, it's a very basic function, but we could say, well, there's a little bit of duplication between both of these functions. They both have a greeting and then the name. So we could dry it up a little. We could create a greet function that takes both the greeting and the name, and it returns greeting and name concatenated together with a comma in between. And then our greet in English and our greet in Spanish functions just have to delegate to that function. They both take a name and then they call greet with the appropriate greeting and a name. And so that works fine. In fact, this is a great functional approach. We just have a generalized function, and we have these more specialized functions that call to it. But we still have to deal with a little bit of the boilerplate of each of these functions explicitly accepting that name argument and then passing it on. And we can actually use another trick from functional programming to remove some of that boilerplate. So I'm going to rewrite this greet function. I'm going to introduce two arrows in my arrow function. Now, if this looks unfamiliar, let's break it down. So what's happening here is instead of taking two arguments, I'm only taking one argument at a time. So first off, I have a function that takes the greeting argument, and it's going to return a new function instead of returning my result. That new function it returns is going to take the name argument. So one argument at a time. And it's this new function that will then return the final result of greeting concatenated with name. So the benefit I get out of this, though, is I can then call that greet function once, which means I'm only supplying the greeting argument, and it provides back that new function that accepts the name. And I essentially am just going to configure this generalized function into a more specialized function. So when I call greet with hi, I get back a function that's going to prepend hi when it receives name. And same thing with hola with the greet in Spanish function. And then when I call greet in English with the name, it'll have both arguments finally supplied, and it can return back the final result, hi lambda squared. And with greet in Spanish, I do the same thing, but I'll get back hola lambda squared. So this concept is actually called curative. So this idea of taking a function and letting it only accept one argument at a time is a curative function. And then when I call this function, normally when we call a function, we say we apply arguments to it, and then we get back a result. But in this case, I haven't applied all of the arguments, so I'm partially applying arguments. When I call greet with just the first argument, I partially applied the greeting and sort of filled that in. It's not until later that the function I get back, when I call it with the name, I get back my final result. Now, this is such a prevalent concept in functional programming that it actually comes built into a lot of languages. So now, this morning, we're going to look at some Elm code. So this is our greet function in Elm. Fairly straightforward. We have a greet function. It takes a greeting and name arguments. In this case, we don't have parentheses or anything like that for our arguments. We just use white space. And then we set the function equal to an expression. So in a lot of functional languages, we have this idea of expressiveness. We don't have tons of statements and a return keyword, but rather we just let it be equal to whatever the final result needs to be. And that lends itself to more terse functions that are enforcing the single responsibility principle a lot well. But the thing I want to focus on here is this function in Elm already has that curried concept built into it. So it's not accepting two arguments, it's accepting one argument at a time, actually. So when I call a greet down here with one argument, in this case, I'm calling greet with two strings, hi and hola, and we use white space in Elm to call our functions. I'm going to get back a new function, just like we saw with the arrow functions in JavaScript. And it's not until later, when I call these new configured functions that I partially applied, that I have now supplied all the arguments and I get back my result. So like I mentioned, this is prevalent in lots of functional languages. Elm, PureScript, Haskell, OCaml, a lot of the MLs definitely. So this also goes back to the idea, what we've been looking at, of functions as building blocks. So what we've been doing is with these create functions, we have very generalized functions. And we can create more specialized functions out of them by partially applying arguments. And that lends itself to us not having to write as much code as we used to do. So it's easier to dry up our code through curried functions. Then moving on to that, there's other ways that we can help with too much code. And in this instance, it's not a problem of don't repeat yourself, but it's a problem of a function that has too many responsibilities. So I have a create order function that's going to take a shopping cart and a customer, and it's going to return an order based on this information. So the first thing it's going to do is it's going to compute a total. We'll start off with a total of 0. Then it's going to loop through all the shopping cart items and add in their price to the total. Then it'll loop through all the discounts and apply each discount. We'll apply a shopping cart tax, shipping costs, and then finally round it to 2 decimal places. And then once we have that total computed, we can return this new order along with the customer and that total. So the problem here is it's a basic function, but we have this idea of this function is doing a lot of steps to compute that total. It has a lot of responsibilities. And that can make the code harder to follow and harder to understand. So it would be nice if there's a way from the functional world that we can kind of fix this and make it more understandable and kind of delegate out a lot of these responsibilities. So to do that, let's start off by looking at a simpler example, and we'll move back up to this function. So I have this excited greeting function I want to write. It's going to take a name, it's going to convert it to uppercase, then it's going to say hi, name, and then it wants to put an exclamation point at the end of the function. It's very straightforward. But I want to apply this idea of taking special generalized functions, combining them to make this more specialized excited greeting function. So I'm going to write some helper functions. The first one will be a toUpper function. It takes a string and it delegates to the string's toUppercase method. I'll also have my greet function that we wrote earlier, the curried version. And then we'll have this exclaim function that just takes a phrase and it appends an exclamation point. So if I wanted to combine all these functions together, I'd probably have to write something like this. So we take the name argument, we pass it into upper, so we convert it to uppercase. The result of that, we then pass into greet. Note that we have to call it twice because it was a curried function, so we apply the hi, and then we apply the result of toUpper with name. And then finally, the result of that will pass into exclaim. And so this works. We've combined those functions in a functional manner, and when we call excited greeting, we'll get hi lambda squared with the exclamation point at the end. But the problem with this is that code is kind of hard to read. We have a lot of parentheses. This has a lot of Lisp in here right now, so it'd be nice if we could fix that and make this code a lot more readable. Well, we can actually do that with another great functional concept. So I'm going to bring in a library called Lambda. We could also do this with Lodash if you're more familiar with it. But Lambda has a lot of functional helpers for writing functional JavaScript. So I bring in Lambda, and I'm going to use a function called pipe. So this pipe function, what it does is it takes a variable number of functions and sort of wires them up together so that the result of one function will become the argument or input to the next function as you go down the pipeline. So I call it with my 3 functions. It's going to return back a function. That function is going to take the initial argument. So we're going to start off with the name argument here. And then it's going to just pipe that name argument through each function one at a time. So when it goes through toUpper, we'll get lambda squared in uppercase. Then it'll go into greet. Notice I can write this in a really nice manner because I curried the function, because it's giving me back a function that wants the name argument. So I'll get hi lambda squared. And then finally that gets piped into exclaim to add the exclamation point at the end. So the nice thing about this is not only do we have fewer parentheses, but we have this very readable syntax where we see how we're chaining from one function to the next to get our final result. So this goes by another name in the functional world, which we call function composition. So this idea of piping things together, letting the result of one function become the input to another, is called composing functions, or sort of composing, piecing them together. And again, because it's so prevalent in the functional world, it comes baked into a lot of functional languages. So if we had our Elm example here, we write our greet function and our exclaim function, and then we can have our excited greeting function that we had previously in JavaScript. It takes the name argument, but then I'm going to use this interesting operator here. So this is known as the pipe operator in Elm. It's also available in languages like F#. And what it does is it takes the left operand and it passes it in as the last argument to the function on the right. So you can think of it similar to Unix shell piping if you've done a lot of shell scripting. So we're going to take name, And we're going to essentially pipe it through into string to upper and get our lambda squared in uppercase. That gets piped through to the greet function with high, and we get high lambda squared. And then finally exclaim again, just like we had with the lambda's pipe function. So this is baked into the language, so it ends up being a lot nicer and cleaner approach, and we can see this clear distinction of chaining one thing to the other. You can think of this also in terms of when you chain methods on JavaScript objects. So now that we got an understanding of this idea of piping or function composition, we can revisit our create_order function and think about how could we break it apart and move these responsibilities out. Well, we could take this whole piece of computing the total and we could just break it apart into well-named functions and use the R pipe here to apply every function one after the other. So we start off with our pipe, we apply all the functions, and we provide the initial total of 0. And then that 0 is just going to get piped through each function and will accumulate the total with each and every step. And what's nice is now we have all these well-named small functions. We can put them together to create more complex functions. So we can use them within other contexts in our application. And now our code is going to be easier to read, easier to understand. So now, our fifth problem. It's scary to refactor my code. I'm sure we've all dealt with that, especially in larger code bases. So if we return back to the create_order function that we just wrote, and let's say now that we have really got on the gung-ho with the idea of currying these functions, we find that it would be a little more ergonomic to transform the create_order function into a curried function. And let's also switch the order of arguments. So we'll take customer first and shopping cart next. But let's say we miss one of our call sites in our code base and it blows up. We're still calling create_order with shopping cart first and a string for the customer as the second argument. So is there something we can do to fix this? Well, we can actually bring in strong static types to deal with this issue. So this is obviously not a functional programming only concept. Static types exist in lots of other languages that are not functional. But many functional languages are closely tied to using strong static types for building your application and then having compilers that enforce those types. This could be languages like Elm or Haskell or OCaml. So if we were to apply this idea, we could revisit the create_order function. And let's say if we implemented types, and because it's a compiled language, this compiles to JavaScript, well, the compiler is going to catch that for me, and this will never become an issue in production. So it's going to detect that I'm calling these arguments in the wrong order. It expected, or saw a string in the second argument, but it really expected this record that had discounts, items, and so on, which was our shopping cart record. And so this is going to prevent any issues for our users in production because the compiler was able to infer, based on our usage, what was the static type at compile time. So we could just stop right there. That's a very compelling case for static types in that they can prevent lots of these simple issues that come from refactoring. Imagine in a larger code base, it can be really daunting or scary to refactor a ton, especially if you don't have good test coverage. But there's also other benefits we can get out of static types. So one of the more simple ones is through type annotations. So far I haven't mentioned or shown any of these types in Elm. That's because it infers types. But we can actually provide type annotations to describe what our expectations are about the values we're using. And the benefit of this is it's going to be good documentation for you and your team. So I don't have to read through the definition of a function to immediately know what are its arguments or what are its result or return values. The type annotations, I have clear documentation of what those things are, and that becomes easier to grok and understand the code more quickly. On top of that, when we want to think about making our applications domain-friendly, a lot of functional languages that support strong set types also support custom types that allow you to create types that are going to refer back to things that make sense within your application's business domain. So if we go with our theme of a shopping cart, in Elm I can use something called a type alias, and there are different affordances in other languages where I can create a type and let it sort of refer to some other type. So in this case, this would be a shopping cart item, and I'm going to say this type refers to a record, and that record just has a property called price, and that is a float. I can build on top of that, I can add a shopping cart type alias. It has all the fields we would expect in our shopping cart, and it can even refer back to that item. I can say it has a list of items in this type. And then I can finish up by creating this type alias for an order. So we have the status, we have a customer, and we have the total. But what's nice about going through all these steps of creating these type aliases is that now back in my create order function, I can refer to those types. So now this code makes sense within my business domain. If I'm reading the code base, I can see, oh, Preorder takes a shopping cart. That's a specific type of thing within my application. And it returns an order. So this becomes better documenting code within your domain. Now there's another way we can also build upon this idea of custom types. So if we return back to this order, I'm using a string for the status. And that may not seem like a problem, but within our domain, we might say status can only be maybe 3 values that make sense. But if we're using a string, as far as the type system is concerned, any string is valid. That means a string of random characters or the empty string. But that doesn't make sense in our application. So we're going to need lots of runtime code to verify that status is a valid value. It would be nice if instead we could harness the type system to ensure that only valid values can exist in that status field. So we can actually do that with something called a union type. It may go by other names like a discriminated union, you may hear algebraic data types, but it's this idea of creating an entirely new type with its own values. And if that sounds really mind-bending, just think of this as an enum, if you're more familiar with a object-oriented language like C#. So I can create an entirely new type called status, and then I can provide values for it, kind of like enum values, and say it's either new, processing, or shipped. But what this gives me is that from the type system's perspective, I can ensure that status can only be one of those 3 values now. I don't have to worry about a random string of characters or an empty string. And now I can return back to my order type alias, and I can say status is of type status. And the type system and the compiler will know only those values are valid. So here I can swap out the new string with this new value that the union type introduced for me. So now on to our 6th and final problem. Everyone's lovely data type, the null. So let's say we're working on sort of a social networking application, and we have this get best friend location. It takes an ID for the user, and then it takes a user's map. This would be, in this case, with JavaScript, it would be an ES6 map, kind of like a hash from Ruby or a dict from Python. So I'm going to first look up the user by ID. Once I have that user, I'm going to look up that user's best friend by calling users.get with the user best friend ID. And then finally, I'm going to return this friend's location. So this seems all well and good. But then in production, I run into this issue. Uncaught type error, cannot read property best friend ID of null. So we probably all encounter null reference errors, and they've bitten us in many, many ways in production before. So if we return back to our implementation, we realize, oh, I'm getting this thing out of a map, but I have no guarantee that the user might exist. So user could be null here. So what do we have to do? Well, we'll wrap it in an if statement. So if there is a user, then we know everything's safe to proceed. But then what if the user doesn't have a best friend? Well, that could be null, and that's really sad, unfortunate. But, well, that's a null, so let's guard against that. And, well, the friend is coming out of the map, so they may not exist, so that's another null. We have to guard against that. So So we've probably all dealt with code like this, and it's really annoying. So as our code base grows, we have this potential for more and more nulls to just kind of pop up. And so we have to do our due diligence to find all the possible nulls. It's kind of like finding Waldo, except this is JavaScript, so everyone's Waldo. But that leads to the issue where we're just having to hurl these if statements everywhere if we're going to be defensive programmers. And that can get really disheartening, it can get really annoying, and that's probably why we abandon it so much and just trust that null's not going to happen here. So can the functional programming world help save us from this tyranny of null? Well, there's actually ways with static types in functional programming where we can deal with this. So a lot of functional languages have this type called maybe, or option. And it's our way for representing the presence of or absence of a thing. And so in Elm, the maybe type looks like this. It's a union type, just like we saw earlier with the status type that we created for our orders. So it has two values. First one is nothing. And nothing is essentially our replacement for null. But this is a value of maybe, so it is of type maybe. Think of it again just as a new value for maybe. Now if I do have something, I don't have null, then I'm going to have a just value. And these values for union types we also call constructors. So you'll notice here we have just, and then we have this lowercase a next to it. So these constructors or values can also take arguments themselves, so they can actually be constructor functions that create an instance of the maybe. In this case, this lowercase a is something we call a type variable. And really that's just a fancy way of saying that I can have maybe of anything, of any other data type. So a is just kind of a fill-in for string or integer or anything like that. In fact, if we visualize this, we could think of just as sort of a box that's going to contain something. So if I had just of the number 42, it's like a box that contains the number 42. If I have just of the string high, it's a box that contains the string high. Another way to visualize this is to think of maybe as an array or a list. And this is a list that can either contain nothing or it can contain only one thing, but it can't contain anything more. So just of 42 is like a list or an array that just contains the number 42. And then nothing is just like the empty array or empty list. So let's apply this idea of maybe to solve that earlier issue of finding a best friend's location. And we'll start off with a simpler example. So let's say we just want to take a user and get their name. So I'm going to write this in Elm because it has the maybe type. It's going to take an ID, and this type could be just a type alias to int. It's going to take a data type called a dict, and this is just like a hash map or map from JavaScript, a dict from Python. It has keys, reference values. And then finally it'll return a string, which is just the name of the user. So there are functions built into Elm. In this case, I have a dict.get function that takes the key and then the dict, which is the users in this case. And it's going to return a user, but that user may or may not exist, so it's going to return maybe of a user. It's essentially going to return a box that might contain a user. So if I want to get at that user, though, I need a way of accessing what's inside of the box. So with functional programming, we have this idea of pattern matching. And in Elm, we use something called a case expression to do this pattern matching. So you can think of a case expression as sort of a souped-up switch statement from JavaScript. So I'm going to say case dict.get ID users of. So it's basically case is accepting the maybe user as an argument. And then what I'm going to do is I can provide branches to sort of match whatever the result of this is. So if I get back a user, I would expect that to be inside this just, so I'm going to match on just user. And with pattern matching, not only can I match that it was a just, I can also unwrap the just and pull out the user. So I get access to the user, and then I can return the user's name. So visually, it's like I've opened up the box, and I've been able to access the user and pull them out and then do something with it. In this case, return their name. So now, we could just say, let's leave it at that, we're all well and good, we don't have to worry about null, it's not going to happen. But if we try to compile this, because it's a compiled language with strong static types, it's going to blow up. It's going to say this case does not have branches for all possibilities. So what's happening here? Well, one of the benefits we're getting out of a language with strong static types and these discriminating unions, union types, is that with pattern matching, it can detect if you're not handling all of these possible branches. So in this case, it knew that I'm dealing with a maybe. That means nothing could possibly exist, but you're not handling it. So essentially, it's ensuring that you always handle null, even if you think it's not going to happen. And that's going to prevent those bugs. So now we can go back to here. We can add a nothing branch. And in this case, we'll just say return an anonymous string for this use case. And then it'll compile. We're handling null, and everything's fine. But now what about our original function? That's the original problem we wanted to fix. So if we were to rewrite this in Elm and use pattern matching, we would end up with something like this. And that's a lot of pattern matching because we have a lot of possible maybes. And I don't know about you, those ifs were looking pretty good earlier. So does that mean functional programming isn't a good solution to this problem? Because it's not very ergonomic. Well, there's actually a different way we can write this with functional languages. So I can actually reduce it down to this. So we still have a getBestFriendLocation function. It takes ID and users. We'll still call dict.get with the ID users. We know that returns maybe of a user. But then I'm going to use that pipe operator we learned earlier, and I'm going to pipe it into something called maybe and then. So that's something new and probably a little confusing. So what this maybe and then function does is it's going to take another function as an argument, as well as the maybe value. In this case, we have maybe of a user. And what it's going to do is it's going to handle that pattern matching for you. It's going to detect if it's a just. It's going to use the function you provide. It's going to unwrap the user and provide it as an argument here. And then you can return whatever you want out of it. In this case, I want to return best friend ID, which happens to also be a maybe of an ID. And so what maybe and then is going to do is it's going to take that new maybe you return and just swap it out. So that when we hit this line, now we're dealing with maybe of an ID. Now, if we had a nothing earlier, it just would have ignored it, and it wouldn't have bothered calling the function. So nothing would have blown up in your null situation. But we'll say we have maybe of an ID here. We'll pipe it in again to maybe and then. In our function, we'll get the ID. Oops, sorry. And then we can call dict.get with that ID. And that'll return maybe of a friend. So we'll replace maybe of a friend with the maybe of ID. And now we have maybe of a friend. We'll call maybe and then a last time to get access to the friend and return their location, which may or may not exist. So it's always important with maybe and then, this inner function has to return another maybe, and it's just going to keep replacing it. If you're familiar with JavaScript promises, this is very similar to the then method on promises, where you can return a new promise inside of your then callback. So I have to apologize a little. I kind of ribbed on monads a bit earlier, but you kind of sort of just learned what a monad is. Now, there's a lot of nuance to it, but this idea of chaining together these functions with maybe, and they could possibly fail, but you don't have to worry about is it just, is it nothing, I just care about my core business logic. In the essence, that is what a monad is. You just want to chain these operations together to accomplish your ultimate goal. So let's recap what we've covered. So we talked about hard to test code. How are we able to solve that? Well, we introduced pure functions. We know they take an input and produce a certain output. That's really easy to test. We had hard to follow code. And we saw that's from just providing tons of instructions, imperative code. We can swap out for expressive and declarative code and really declare what our true intent is in our applications. When our code breaks unexpectedly, that's usually from mutable data. So we can swap over to immutable data. In JavaScript, we could use something like object.freeze. In languages like Elm, it's already built in. When we have too much code, well, we can use curried composable functions that we can just combine together in different ways to make more complex functions and delegate out responsibilities. If it's scary to refactor our code, we can use strong static types. You can either reach for a functional language like Elm, or if you're in JavaScript, you could use something like Flow or TypeScript to accomplish something similar. And then when we're dealing with null, we can use types like maybe and use concepts like monads, where we just chain together operations. And we can do that in functional languages, or there are also libraries that let you do things like maybe in the JavaScript world. And that is ways to apply functional programming practically. There's a link to my slides. Thank you all so much. I appreciate your attention.